Okay, lady and gentlemen, there's only one lady. Please don't disturb. You know, I know there's one lady, but it's you're from China also.
Yeah. No, I'm from Denmark.
Okay. Nice to meet you. Okay. But please, since the time is going very fast, and today in this session we have unfortunately one paper more. We include the paper number from the section 6B1, which is shifted to the section that will be presented at last. Therefore, the first speaker is Mr. Jozef Ritonja from that's the Faculty of Electrical Engineering Computer Science, University of Maribor, Slovenia. Please you have 15 minutes all over. Therefore, 12. I think the 12 for presentation and 3 for discussion.
Yes, thank you.
Okay, please go ahead.
Ladies and gentlemen, I hope that there will be one paper less, but okay, I will try not to be boring. I will skip some equation, and I would like to motivate you for this paper to read it later and perhaps to continue work and to use the solution of this work also in your papers. What will I do? What will I explain today? The main question is how good are simplified mathematical models for dynamical analysis of the synchronous generator connected to the grid. Let me first answer on some sub-questions. Is this problem important? Yes, it's very important. Why? Because the oscillations are very harmful. Where we can see this? You can see this in losses, and you can see this in blackouts of power systems. We had in last year a lot of blackouts. 4 years ago, we had the largest blackouts in the history. More than 1 billion people were affected. What are the reasons for these oscillations? First, the changes in construction of synchronous generator, and after then also the additional control systems in power systems. So both together are the problem, and which are the model solutions for this problem. So one of the solutions is that we try to analyze synchronous generator prior to manufacturing. And the other possibility is that we can implement additional control system for damping and stabilizing if the synchronous generator is already built and installed into the operation. So, but for both solutions, we need dynamical mathematical model, and therefore is this topic so important. Are these models already known? Yes and no. There are many mathematical models of synchronous generator, but the majority of this model is not suitable for analysis of oscillations. The main reason is that from theoretical point of view this is no problem, but for practical work it is very difficult to obtain all parameters of synchronous generator which are necessary, which are requested in these models. And second problem of the models is that the model structures are quite complicated, non-linear, and therefore it is not possible to use linear analysis tools and tools for design and synthesis of control systems. So, a short survey. The basic mathematical model of synchronous generator is well known, 7th order non-linear Deco model. On the other side of the list we have the simplest one, voltage behind synchronous reactance model, and between are many simplified models which are more or less accurate. Some of these simplified models are written here. So, and during my presentation I will present and compare two models. The basic one for the reference and the linearized third order model, called also Heffron Phillips model. This model is important because it has very good ratio between complexity and accuracy. Let's start with the nonlinear model. In this case we assume 6 stator windings, 6 windings, 3 on stator side, 3 on rotor side. We assume that the synchronous generator is connected to power system, to the network. Inputs of this model are mechanical torque and produced by a turbine, and rotor field winding voltage produced by excitation system. Model is written in state space form. We need 7 state space variables, 5, so we can see here again, 2 inputs, 5 linkages, and 2 mechanical state space variables. But the main problem with this model is that it requests a lot of parameters for synchronous generator. The manufacturer, they don't give us these parameters, and it is also very difficult to obtain, to measure all these parameters. Additionally, we need also steady state variables and base quantities for normalizing. Second problem is that the model is not the simplest one. It is written by a system of 7 nonlinear differential equations with many additional algebraic equations. But the good thing is the model is very accurate. So I will show some results from our synchronous generator with nominal power 12 kilowatt. This is small synchronous generator for home power station, power plants. This is our measurement system. Instead of a turbine, we use asynchronous machine with frequency converter. Here are, first we calculate, measure and calculate models data. And here are the results. You can see that the results of simulation and measurement fit very well together. So the upper figure shows the answer, the response of the model and system on the step change of mechanical torque and in rotor speed. And the lower bottom figure shows the response of the rotor speed on the step change of field excitation voltage. So because of these advantages of this model, we tried to simplify it. We made state space reduction first, and after then linearization. Here are assumptions, and finally we obtain linearized third order model. We have the same inputs, but only 3 state space variables and only 9 parameters, and these parameters are much more simple to determine. Here is the model written with state space equation and output equation. Here is the block diagram of the model. We can see that the model is third order. We have 3 eigenvalues, and 2 of these are dominant conjugate complex, and these eigenvalues are linked with the frequency and damping of oscillations. These are already slides prepared for questions, possibly. And here are the answer. Here are the responses of this linearized model. We can see if we use this model instead of full order nonlinear model. In this case, we have the same responses if we simulate it in small neighborhood, small vicinity of the equilibrium point. Here is the response to the mechanical torque, step change in speed, rotor angle, and stator voltage, and here is the response for the change of field excitation voltage. So in all cases we have very good dynamical and steady state accuracy, but for larger input deviation, linearized model is not accurate. So we can see the deviation in steady state and also in dynamical performances for larger step change in input variables. So for 50% from nominal value. This is the first was for mechanical torque, and this was for field excitation voltage. So what to do? So we would like to answer on the question: how is the function of steady state error and dynamic error on the deviation of input variables? So for our model for 12 kilowatt synchronous generator, we calculate the influence of mechanical torque deviation, and we can see here on the steady state in rotor angle here and stator voltage. So we can see if we change mechanical torque in the range from minus 0.5 pu to plus 0.5 pu, our steady state error is changing in this area. So if we will stay in this range plus minus 50%, the steady state error in the rotor angle will be less than 15%. And similar is also for voltage error. And here are the calculation, here are the results. Here are the results of the influence of excitation voltage deviation on rotor angle and stator voltage, steady state error. In the previous case it was mechanical torque, and here is field excitation voltage. And finally also the influence of input deviation on the dynamic accuracy. So we use integral squared error, performance index. So, and here are the results. So all these results were valid only for our synchronous generator, but is it possible that to obtain some general conclusions for majority of synchronous generator of different nominal powers? So therefore we made analysis of about 40 synchronous generators, different nominal powers and different types, and we obtained in almost in all generators similar shape, similar form of these functions, of these graphs. So, and these are the forms only for 5 synchronous generators. So for these 5 from 25 till 1915 MVA, and these are the forms, these are the graphs which shows the steady state error in rotor angle and stator voltage for different excitation voltage for these 5 synchronous generators. This is for dynamical error. What can we, which conclusion we obtained from our study, from our analysis? First, some qualitative conclusions. We can say that for all synchronous generator, the steady state error is in stator voltage always smaller than steady state error in rotor angle. Second conclusion is that the impact of mechanical torque on steady state error is always larger than the influence of the excitation voltage, and the same is also for dynamical error. Can we say something about quantitative conclusions? So we try to formulate it in such simple way. So we can say that if we change mechanical torque, if the mechanical torque deviations are smaller than 30% around the equilibrium state, then the steady state error in rotor angle will be smaller than 10%, and steady state error in stator voltage will be smaller than 5%. And this will be valid for the majority, for all analyzed synchronous generator, and these were really a lot of many. Similar conclusion we can obtain also for excitation voltage deviation. During our analysis, our study, we obtained a lot of experiences in this area. So therefore, we would like to write a kind of guides, a table with guides, which model is better for different situations. So we try to analyze which model is better considering accuracy in small operating range or in large operating range, which model is more simple, which model is better, is more suitable for numerical simulation, which model is better for theoretical analysis, which model is better for control system design. And in such way we brought such table with rules, what is better for every situation. The goal of this table is to have the engineers and researchers to decide which model is better to use in any situation. About the conclusions, so during the presentation, it is not written in the paper, I tried to motivate you to show that the problem, the topic of the paper is up to date, is really important. The main contribution of this paper is to show the quantitative and qualitative analysis of both models, the advantages and disadvantages of different models, and with the goal that I will that the researcher and engineers can improve choosing, so selecting the best model for the best support situation.
Thank you.
Thank you.
Thank you. Thank you for a very interesting presentation. I will start to pose the questions. Who from the audience will have the questions? One more questions. May I have a question? That's a very interesting thing, since in your title is applicability. If it's applicability, it should be confirmed by some experimental results. You know, that's the most simply, they often use the Park-Goriev equations, we just use up to now, and we measure these things, therefore there are some equations done. You probably, in your system, you neglect the saturation, also you assume the power system is equal to infinity, is right? Therefore there's some simplifications. But you had a chance to measure it, since you show us some model. And did you check the measuring results, some widgets were able to measure it with your the theoretical? Since in this is we have magnetic system. Therefore, if we have magnetic systems, the probability theory doesn't work. We cannot extend it for high power, since that's non-linear system.
Yes, first thing, yes, we neglected saturation, and we think that
influence
infinity
of the system.
Infinity
Yeah.
us. We compared our simulation results only with this one synchronous generator, the small one.
The small one.
Yes.
Okay.
We didn't have the possibility for.
Okay. Okay. Thank you very much. Since time is already but who would like to say something? Or, okay, we can say thank you very much. Okay, the next speaker is Professor Czapp, was I not wrong? Okay, and with the new method for the load compensation used during creation of post-blackout start-up pass and power system. Please go ahead. 15 minutes also.
Thank you very much, Mr. Chairman, dear audience. My name is Stanislaw Czapp from Gdańsk University of Technology, and I'd like to present a paper which considers blackout and restoration of power system. We are used to the electricity very much. We cannot imagine our life without electric lighting, electric power, electricity, but some accident may occur that we have a blackout. These are the examples. Due to extreme weather condition in Poland in 2010, due to rain and ice, medium voltage power line collapsed, and we had a blackout, respectively small area of Poland. This accident was much serious. In 2008, due to extreme weather condition, the towers of extra high voltage power line collapsed, and we had a blackout on the large area of Poland. If blackout occurs, we want to restore power system, power plant, switch on power plant as far as possible. Generally, we use a hydropower plant as a source of power, and we want to start a thermal power plant. And we have to create startup path with the use of high voltage power line. In Poland, we have 110 kilovolts overhead power lines, 220 kilovolts, and 400 kilovolts power lines. It is not easy operation, and if we analyze papers which discussed this problem, we can say that the following problems are considered: protection relay settings, coordination of and communications of power system dispatchers, turbine governor operation algorithm. But two important issues are omitted, and we propose modification in the operation, the preparing of startup path, the operation of under-excitation limiter, and proper settings of load compensation. Both issues are connected with automatic voltage regulator of synchronous generator. When we have normal operation of a power system, we have loads in power system, and when we switch on consecutive over power lines, when we rearrange configuration of power system, we switch on these power lines on load condition. But during creation of startup path, we switch on consecutive power lines on no load condition. Over power lines are characterized by charging reactive power, so we have a problem with voltage increasing. And during this operation, we cannot cross the border for synchronous generator. Let's look at the example. We have a hydropower plant. We switch on first power line, and then we move to the left on the PQ diagram. Voltage rises. Next power line, more reactive power. Next power line, more reactive power, and next power line. We crossed action border of under-excitation limiter. UL is activating, and we have the effect of UL, very high voltage. So if we analyze the effect of under-excitation limiter, we can see that when this limiter is enabled, we have a problem with voltage level. So we propose to disable this under-excitation limiter when we want to create a startup path. This is the first proposition. The second proposition is in load compensation. In normal operation of power system, we try to keep voltage in the proper level at the generator terminal. During creation of startup path, we should keep this voltage at this place. So we want to compensate impedance of power unit transformer, and signal introduce a correction of the reference voltage value. So we considered two possibilities. Load compensation is enabled, is our proposition, and load compensation is disabled, is a conventional approach. When load compensation is disabled, it means that impedance of this power unit transformer perfectly is equal to 0, but if it is enabled, it is higher than 0, it is equal to impedance of this transformer. The same example, these figures present voltage profiles during creation of a startup path. The blue traces represents values of voltage when load compensation is enabled. According to our proposition, it is favorable level. So at this moment, you should ask me: are our proposition advisable? Are correct? The best way to check is to perform power system experiment. This experiment has been performed in Polish power system. And we propose following modification: under-excitation limiter should be disabled, and load compensation should be enabled. We used Żarnowiec pumped storage power plant as a source of power, northern part of Poland. The rated power is 720 megawatts, and we started Koźnice thermal power plant, 1 unit. This is the largest thermal power plant in Poland, 2080 megawatts, and we created startup path The length of this path was over 600 kilometers, and during this experiment we had to keep voltage within the permissible level. For 400 kilovolts power line, the lowest permissible value is this, and the highest permissible value is this, and for 220 kilovolts power lines, respectively 205 and 245 kilovolts. Let's start. We switch on Żarnowiec 0 megawatts reactive power. We switched first power line. The voltage in the next node in Gdańsk was 381 kilovolts. Everything is okay within the permissible level. Then we had to transform to the system with the voltage 220 kilovolts. Next power line, voltage is okay. Next power line, next node, voltage is okay. In this node, we had to desynchronize transformers working in parallel in order to consume reactive power in this place. If we did not this, the voltage at the end of the startup path would be 280 kilovolt, is much higher than permissible level. We have local consumption of reactive power, and at the Kozienice we had 238 kilovolts. It is within permissible level. Voltage profile in Żarnowiec, and at the end of the startup path we had 240 kilovolts. It is within permissible level without load compensation. We simulated this. It would be 254 kilovolts. This figure presents voltage values at each nodes. This trace represents voltage level according to our proposition. Everything is okay, is under permissible level. We simulated voltage level when load compensation is disabled. We had a problem for nodes. It is higher than permissible level. Conclusions. The proposed modification of automatic voltage regulator settings have just been verified in Polish power system. An experiment was carried out last year, connecting pumped storage power plant Żarnowiec and thermal power plant Kozienice. The experiment confirmed that the modification proposed by us are advisable. Thank you very much.
Thank you very much. Thank you very much. It's exactly on time. Therefore, we have some time to have questions. I know the paper is open for discussion. Who would like to say? That's a very interesting experiment, but talking about the load compensation, you are thinking about the reactive power compensation, right?
No, because load compensation is artificial compensation, correction signal in voltage automatic voltage regulator. So we compensate artificial compensation of impedance of power unit transformer.
Okay. Thank you very much. It's very interesting experiment, and it's not easy to do that. I know.
Yes.
I know very well. Okay, who would like to say something? Okay, thank you very much. Okay, the next presenter is a gentleman from Estonia, Imre Drovtar, but I'm not wrong, is right?
Yes.
Okay, and the paper is on the demand side management and the small power systems, the Estonian case study, right?
Yes.
Okay, please go ahead. Also 15 minutes and 2 minutes for discussion.
So, ladies and gentlemen, my name is Imre. I come from Estonia, from the University of Tallinn University of Technology, and I will present a 2-year research project results carried out with the Estonian transmission system operator. The outline of the presentation is a short introduction, then I will give a glance why demand-side management, then the benefits of small power systems such as Estonia, and then the results of the case study that we carried out. And in the end, there is a small conclusion with the insight to the future work. So if you talk about today's power systems, then we have a large share of renewable electricity coming into our grid, which is usually weather influenced. At the same time, we also have open electricity market conditions where everybody has to compete on an equal basis. And at the same time, the renewable energy targets are also pressurizing the fossil fueled power plants to be shut down. And at the same time, we also have urbanization, or where the loads that used to be in load centers are shifting towards weaker parts of the grid. And we have a question with the distributed and versus centralized operation. So in the beginning, the power system was built for centralized operation, so that power was transferred from point A to point B. But now we are in the situation where we can have generation almost from every point of the grid. And with the increasing these stochastic variables in the system, we also increase the need for these short-term balancing power to balance out these fluctuations. And if so far the balancing has been carried out by these large power plants, then by closing them down, we start to have a deficit of this balancing power. And we carried out a research project to map the Estonian consumers' potential to provide this balancing power to the system operator. We carried out 4 measurements at different sites, at 2 office buildings, 1 shopping center, and also 1 industrial site. So why demand side management? We have various measures that we can use. The most simplest and maybe known to everybody is the static demand side management that is organized through regulatory laws, and it is aimed for long-term energy efficiency and conservation. But if we talk about balancing, then we talk about dynamic or short-term demand side management. And here we have 2 possibilities. One is through the system operator with a contract who can activate them, and also active participation from the customer side who is doing some actions according to some external signals, for example prices. And the impact is not so much on energy efficiency or energy conservation, but rather market efficiency, or more efficient market operations and system control. And for the customer, this gives a new business case to optimize their costs. So the demand-oriented and driven power systems are outdated. So we cannot consider that demand is fixed and we have to plan according to demand. Everything demand is actually quite flexible. We have these loads in the system that are actually unused. And we also need to consider the aspect that if we want to have this balancing power, then whether it is reasonable to invest in generating units that are usually capital intensive and is required occasionally for their power and not for their energy, or should we promote demand related resources. So benefits of small power system. If we talk about Estonia, then we are relatively small and in size and in capacity, and it gives us a great chance to study it in a smaller region. At the same time, we have all the same problems as big power systems. So we have high concentration of loads at different parts of the power system. We have distributed generation near the shorelines where we have wind. And then we also have large centralized production in the eastern part of Estonia. At the same time, the balancing services capacities in the last couple of years have mainly remained below 40 to 60 megawatts. It's quite rare that we need higher capacities for balancing or for system services. And we also have extra motivation from the energy-intensive customers, because if we take, for example, wood industry, then they have to compete on a global market, meaning that if the energy part of their product is higher, then they are less competitive on the market. So here is an example, the additional cost in addition to the electricity price in comparison between Austria, Sweden and Estonia. And we can see that in Estonia, the total additional cost for electricity is much higher than, for example, with other countries where the wood industry has to compete with. So the consumers are motivated to find new solutions how to lower the energy part of their production cost. If we go to the wood industry in Estonia, then it can be described as a high share of induction motor load. More than 95% of the load is induction motors. Then the continuous manufacturing process has incorporated several intermediate storages, which can be used as a sort of energy storage if we want to shift certain parts of the loads. This gives them a certain level of flexibility. And the main constraint from the industry comes from the final production output, which has to be constant. So if the demand side management action would harm this, then it is not very motivating for them. But at the same time, additional flexibility comes from the fact that they have 20 to 27% of reserve capacity in their production lines, which is not used. So even if we turn off a certain part of the production line, they can increase its power output or electricity consumption after the demand side management action, and therefore a bit catch up the production quota. And we determined, based on the interviews with the paper industry, who was not willing to participate in this research project but was kind enough to provide us information, and we did extensive measurements at the wood industry, and we determined that the total paper and wood industry would able to provide for the system operator in short term up to 30 megawatts of regulating power. And if we extended the same assumptions to the rest of the industry, we got a 35 megawatt potential. However, it should be researched further, because we don't know their limitations and restrictions. If we go to office buildings, then the two types of office buildings that we analyzed one was a 24/7 type office building, meaning that people are constantly there. There are 8-hour shifts or 12-hour shifts, and this type of office building also incorporated a small data center. And the other office building was a more traditional, like that is where the work is from 8 to 5. These buildings can be explained that they have large share of heating and ventilation systems, and the proposed demand side management solution would be to control temperature or airflow in the rooms, either according to market price or if the system operator requests. And actually the only constraint that comes from here is the employee comfort. So we have to consider that if the room is too cold or too hot, then the employees, the work output is much less. And we determined that with a duration time of 1 hour, the 8 to 5 type office building could provide up to 72 megawatts of load, and the 24/7 type of office building 14% of load. The data center in this case was not considered as a controllable load, because its service was essential. In shopping centers, again, we measured that the largest share of electricity consumption goes to either outdoor lighting or indoors for heating and ventilation, and also cooling and freezers systems. And the demand side management option was proposed for them to control the temperature of the freezers And there the constraint came from food safety. So in shopping centers, they have to monitor the temperature of the freezers and coolers quite strictly to guarantee that the food is safe for consumption later on. And another constraint came from the missing cooling storage. So if the shopping center doesn't have incorporated, for example, cool storage for these load shift periods, then they can provide only 7 megawatts for demand side management, but together with storage, it would be up to 26 megawatts over the whole Estonia. So, and the installation of this cool storage would have a payback time of 5 to 15 years, depending on the electricity price. So, if we talk about the conclusions, then we can see that the loads can provide a high durational and also variety of services for the system operator. There is a motivation and interest from the consumer side to participate in such programs. And even if the system operator is not interested in the service, then there is definitely a business case for the consumer. And actually, pilot projects similar like proposed here are already in action in Finland. They started, if I'm correct, last year in January. And the system operator in Finland uses, for example, shopping center coolers and freezers for frequency reserves. And there the capacities begin from 0.1 megawatts. In the Estonian case, unfortunately, the system operator minimum requirement is 5 megawatts. So this is also one drawback in Estonia that needs to be dealt with. The problems, no communication and no information for the customers. They don't know what are expected from them, and they are afraid that it will affect their primary business. Lack of aggregation service. So as the TSO requires 5 megawatts and majority of the business cannot provide these kind of capacities, then without these services, the TSO is not interested in the loads. And also outdated market mechanisms that favor generators to provide balancing and system services. And of course, the possibility to need additional energy storages in case of, for example, shopping centers. And from this research, the research group decided to go forward with studying the possibility to provide voltage support in weak parts of the power system through demand-side management with industrial loads. And this is currently ongoing and hopefully soon will be published. Thank you. And
Thank you
questions?
Much. Thank you very much. Thank you very much for the experience. The discussion. But I struck the most that the cost of energy, electricity cost is extremely high in Estonia. Is the same, the price of electricity is also for the consumers so high as the cost, or is reduced?
No, in Estonia it is so that there is this rule of equality, so that everybody has to pay the same price. So whether you are end consumer at home or a large industrial consumer, it doesn't matter how much you consume. It's everybody pays according to the tax. Yes.
Okay. And you base on your own energy with the power plants, or do you have to import energy from somewhere?
Today we have the possibility to cover the whole load with our power plants, but after 2024 Estonia will turn into importing country.
Okay. More questions? Okay, thank you very much. Thank you. Thank you. And the next presenter will be Dr. Leszek Jarzebowicz. Please go ahead. It is on the angle tracking observer for filtering rotor position estimation in sensorless electric drives. Also 15 minutes for all this presentation and discussion. Please go ahead.
Thank you. Good afternoon. In general, sensorless drives do not use mechanical sensors, so they do not measure rotor position or speed directly. Instead, they have specialized algorithms to compute these parameters. And these estimation algorithms in general use other measured quantities, typically motor currents and sometimes motor voltages. And if we have some disturbances, some errors in measurements of these electrical quantities, these errors are reflected onto the estimated position. So, for instance, if we have some random error in electrical measurements, it corresponds to some noise in the position computed based on the estimation algorithm. In general, the estimating algorithms can be divided into two groups. The first one, I called it model-based approach, namely observers. It depends on some mathematical model of the motor with supplemented with some correction function, and this approach has some natural way to filter the disturbances, because the state variables in the model are integrated, and moreover the sensitivity to measurement noise can be controlled by adjusting gains in feedback matrix. And the other group, I called it parameter-based approach, computes rotor position, but by identification of position-related parameters. Typically, such parameter is stator inductance, which depends on rotor position. And in this case, position is derived directly from single identification. Therefore, these estimators are sensitive to measurement noise and require some kind of low-pass filtering of the outcomes. Low-pass filtering, in turn, introduces some lag, but in most cases these estimators are used at low rotor speeds, so this lag is not an issue. And our goal, our main aim, is to filter the noise in the position signal provided by parameter-based estimator, but such estimator which is dedicated for high-speed operation. So low-pass filtering, typical low-pass filtering, wouldn't apply here because of the lag. And we want to, our goal is to first to minimize the peak error in the position signal, and secondly, we would like to minimize the computations time. We want our solution to be simple, to be fastly computed. And we have proposed to replace low-pass filter, typical low-pass filter, with so-called angle tracking observer, shortly ATO. This solution is well known, but in different field. It's commonly used to deliver angular position from a position transducer called resolver, which delivers two signals, one corresponding to cosine of rotor position, the second one corresponds to sine of rotor position, and these signals are also modulated. So this is a typical diagram of such resolver to digital converter using ATO, which is typically produced as an integrated circuit. Such solution have been improved many times. We can find many papers which improve this structure or some of its components. We can also find papers which proves which proves, that this solution can be also done in software, in the main processor controlling electric drives. And we have found one paper which used angle tracking observer, so this solution, to filter the noise from the results of estimating rotor position. But the estimator that the authors applied provided sine and cosine signals by default, so this structure was applicable without major changes. And we propose very simplified structure of such an observer with only 2 integrating blocks and 2 gains, and it's applied to position related signal, not to sine or cosine or both of the position signal. It's easy to implement in software, and we kept second order structure because the references reported that such a structure is able to cancel speed related error. And to verify the properties of our solutions, we have tested it firstly by simulation. Here's the model of our angle tracking observer in digital form. I mean, these computations are triggered with constant frequency clock, and integration is replaced by summing the outcomes. And the model consists also of motor dynamics subsystems, which is composed of some fundamental mechanical equations, including moment of inertia or friction torque and so on. And this model enables us to deliver the true rotor position accordingly to the waveform of set torque. And this position signal is then supplemented with some white noise to model the features of our estimation algorithms and the features of some measurement disturbances. And such model in general enables us to compare the true position, the noise position, and the denoised position, which is the output of our observer. Accordingly to the references, angle tracking observers can face some error components on its output, and these errors are related to speed, to acceleration, and to jerk. Jerk is the derivative of acceleration. So we have proposed some test scenario for our observer, which reflects the worst possible conditions. I mean, the speed range is between 0 and the maximal speed. We have maximal torque, positive and negative, so we have maximal acceleration and deceleration, and we have fast changes between acceleration, deceleration, and freewheeling, which gives us high jerk. And here are some results. In red there is a noise position, and in navy blue there's a position signal denoised by our observer. Of course, the output muchly depend on setting the gains K1 and K2. In general, high gains give us poor noise suppression, and in turn low gains give us a very smooth waveform, but some components corresponding to acceleration and jerk start to appear. So we investigated how the gains correspond to the peak error. So here's a kind of map or 3D chart where on this axis we have K1 and K2 gains, and we can see that we have some area of errors below 1%, which corresponds to relatively high range of gains K1 and K2. These are logarithmic scales, so we can be quite flexible with selecting these gains. Especially we can select the gains to match this condition. T is control period and N is constant. If we do that, we can replace multiplying operation in our microprocessor by bit shifting, which accelerates the computations. And we also have compared our solution with some typical low-pass filters, boxcar and sync filter. And here is a summary of this comparison. In gray color, there is a maximal position error in our input signal, so the noise signal. The red one is the maximal error when ATO is applied, and the other outcomes corresponds to two filters, but they are in two versions. The first version is straight, it's typical, and the later is phase compensated. That means that we are aware what lag, how much lag such filter introduces, and we also measure the speed, so we can cancel this error component related to this lag, and this gives much better results. Still, our ATO appears to be a bit better in suppressing the noise, and it's much simpler in regard to computations, because this filter has to memorize and process over 100 results, and our ATO has only two results of integration. So we have also verified our solution by the means of experiment. Here is the simple code in our microprocessor. It's of course in C language, which does all the job. I mean, this structure is represented, this integration operation is represented by summing, and these gains are represented by bit shifting. So this code is executed in our processor by more or less 20 clock cycles, so it's very, very fast. And here are some results very similar to the ones obtained by simulation. The difference is that the real drive, when we reach so-called base speed, limits drive power, so that the torque is lower at higher speeds, and finally the drive reaches lower speeds, a bit lower speeds, and two position signals. The red one is the noised one, and the navy blue one is the denoised position using our ATO. We see that this denoising is efficient, maybe not such efficient as in simulation, but we are quite content of the results. And some summary. We proposed a very simplified structure of angle tracking observer, some methodology to pre-select the gains of this observer by simulation, and we showed also some implementation issues and verified our solution experimentally. And our ATO is adjusted to position signal, therefore it can be applied to any or almost any position-based sensorless drive, and it appears to be efficient and very fastly computed. Thank you.
Thank you very much for very basic presentation. Any question? A question? You mean about the sensorless drive? You mean that this is the drive who is not equipped with any sensor, right?
No. In electric drives we call sensorless such drives which do not measure mechanical quantities. They still measure voltages and currents, but they do not measure.
Your torque, when you showed that it was calculated based on the electrical quantity, is the voltage and current, right?
Mm-hmm.
You never tried to measure the torque indirectly on the shaft.
No. Typically, we do not. Almost never. We do not measure the torque. Typically, we measure rotor position and speed.
Okay.
And if we need torque for some controlling and other things, we just compute torque.
Okay,
This is
so-
typical. But sensorless drive is a drive where we also do not measure position and speed of rotor.
Okay, just on the calculator. Okay,
Mhm.
thank you very much. Question? Thank you very much. Okay, the next presentation will be done by Viktor Slapak. Imre? Okay, and there's a position controller for PMSM based on finite control set model, predictive control. Also, please, 15 minutes for your presentation.
Good afternoon, ladies and gentlemen. Thank you for the short introduction. I came here from Slovakia, from Technical University of Košice, and today I would like to present you a position controller for a permanent magnet synchronous motor based on finite control set model predictive control. Model predictive control presumes the mathematical model of the motor. Here we use a mathematical model in rotor coordinates, shown here, and for the simulation and the experimental verification, we use a very small permanent magnet synchronous motors with the power about 230 watts. The motor was coupled with a very precise cycloidal gearing, and as you can see from the parameters, the motor has a very high dynamics in both electrical and also in the mechanical part, which is very tricky because we need a very high sampling frequency. It is very hard to obtain such a frequency with the low-cost solutions, but we try to do something with it. Now I would like to say a little introduction into finite control set model predictive control. Also, it is quite known. It is based on the idea that all the power converters have only limited number of switching combinations. In the case of three-phase power inverter, there are only 8 admissible combinations. They can be described as voltage vectors, like here in this picture. Two voltage vectors are 0 voltage vectors, the others are shifted by the 60 degrees. I'm sorry, the main idea behind the finite control set model predictive control is that we can predict the future behavior of the machine for all these voltage vectors. After we have predictions, we can choose the best action, the best switching combinations at that sample. The decision is made by the cost function. The cost function represents our request, if I can say so. In our paper, in our contributions, we examined 2 position control structures. The first one is the pure position SS and PC control. The position is generated by a range generator. And if we have a position reference by the range generator, we also have an angular speed reference and also the angular acceleration. The Kalman filter used in this control structure filters the measured values and is also used to estimate the load torque, because in the predictions we need the load torque to properly estimate the future state. The second control structure is the combination of the PI position controller and the FCS and PC controller. The advantage of this structure is that it needs less computing time, because we do not need a prediction of the position. We only need the predictions of both current components, angular speed, and we need estimated load torque. The cost function itself is very simple to understand. It consists from 5 terms. The first term is express the position reference following. Next is the speed reference following, the current control, torque per ampere maximization, and the speed and current limitation. The limitation is a nonlinear function that gets a very high value when the speed or when the predicted speed or predicted currents are very high. over the maximum ones. So it means if this is very high, the whole cost function is very high, you get very high value, and the controller doesn't choose this voltage vector. The current control reference is made from 3 components that are very well known in the cascade PI control structures. They are described. So the Rotor compensations. This one is not very typical, but it is used to reduce the oscillations in the current waveforms. Next, the viscous friction compensation and the dynamic torque compensation. Here are the simulation results from the MATLAB Simulink. The first is the D-axis current. We can see the small oscillations, but the D-axis current is held on 0 as it should be in the permanent synchronous motor. Comparing to the field-oriented control with the red color, it is very, very similar. In the Q-axis current, we can see where the motor was loaded. It was in the time of 0.15 seconds, and the load was a little bit lowered in the time 0.25 seconds. We can see that the oscillations in the both model predictive controls are a little bit higher than the FOC control. If we look on the angular speed and angular position, we can see that it is almost the same for all 3 control structures. But if we look in the detail, we can see that the model predictive control is quite faster than FOC control. But what is interesting in the position control is the angular position deviation. If we control 4 components with one controller, as we did in the MPC, that it is typical to have a deviation in the dynamic situation and also with the steady state. But when we see absolute numbers, the position deviation is not very large. The experiment was done on the experimental settle, as it's in the picture. There are 2 actuators with the same parameters. They are coupled with the flexible coupling and the torque sensor only for the verification of the torque estimation. For test purposes, we need to design a voltage source inverter controlled by the single microcontroller unit, but with the dual CPU. We need a very high sampling frequencies, so our sampling period was 32 microseconds for this type of control. And the experimental results, we can see a very high oscillation in both axis current. The reason is that the sampling time is very small, 32 microseconds, but the computation time is more than 7 microseconds. So it's more than 30% of the sampling period is only the computation. So we need still a much higher computation power. Here we can see angular speed responses and angular position. As we can see, the pure MPC control has a very high oscillation in the speed response, but the combination of MPC and PI control, it is very similar to FOC control. Also, the position is almost the same, but if you look in the detail, the deviation of the MPC, pure MPC, is very high against the FOC and MPC P control. So, to conclude it, FC's MPC control has brought higher dynamics in the speed controlling, introducing feed-forward compensations, improved a little bit speed and also the current control. The accuracy is very comparable to FOC, but the better results would be possible with higher computation power. So the finite control set position model predictive control can be used as a position control with a little more exploration. Thank you for your attention, and if there are any questions.
Thank you very much. Question? You measure here the torque. What kind of method you use for measuring the torque of the electric motor?
We didn't measure the torque, we estimated the torque by Hellman filter.
Okay, okay.
I can. It
What was
was
the power you estimate of this electrical motor? Rated power you used?
230 watts. Was the,
230 watts.
it was very small motor.
Okay. Question? No, thank you very much. The next presentation will be by Argo from Turkey, Imre. And there's a comparison of heuristic methods for optimum power flow consideration valve point defect with 15 minutes altogether.
Good afternoon, dear professors and colleagues. I am Ahmet Doğan from Erciyes University in Turkey. The title of the presentation is A Comparison of Heuristic Methods for Optimum Power Flow Considered Valve Point Effect. This is the outline of the presentation. First, I will mention about scope of the paper. Then I will mention about optimum power flow and previous studies. Then mathematical formulation of OPF and OPF with heuristic methods. Then simulation results, and then finally conclusion. Scope of the paper is a solution of OPF with valve point effect using different heuristic methods. The methods are which I use genetic algorithm, differential evaluation, particle swarm optimization, and artificial bee colony algorithms. When steam valve starts to open in a turbine, it changes generation curves. That is called as a valve point effect. So we use the cost formulation this valve point effect, and also penalty function is added for generating violations, our formulations. We used IEEE 30 bus system, and we use that system. We compare the convergence curves, and we show the results. Growing worldwide population, industrialization and urbanization will result in an increase in energy demand, as we know. Number of the generation units and the transmission lines are increasing in order to meet that increasing demand. System operators need some analysis tools for optimum and smooth operation of complicated system, and OPF provide us that controlling and optimum operation of the system. The aim of OPF is optimum setting of control variables to minimize the generation cost by satisfying power flow equation, and we do that in physical boundaries. If we look at the previous studies, mathematical based If we look at the previous studies, mathematical based traditional methods are used. These are some methods which are used: gradient method, Newton-based method, linear programming, quadratic programming, interior point method, and nonlinear programming. Traditional methods have some disadvantages. They have some convergence problems for large-scale systems, difficult adaptation to formulation chains, and they spent many memory for the computational. So last year's heuristic methods are preferred. These methods are evolutionary programming, genetic algorithm, differential evaluation, PSO, ant colony optimization, artificial bee colony fuzzy logic, and other methods we can use for solution OPF. That methods have some advantages. They are robustness, flexibility, and they converge global optimum solution. So they are preferred for in last years. These are some studies in the literature about OPF, and I want to present the formulation of the OPF. The objective function fx is the generating fuel cost, g is the equality constraints, and h is inequality constraints. Minimum fx subject to g and h. X is the vector of state variables, can be expressed This is the slack bus real power, and these are load bus voltage, reactive power. This one is the transmission line NVA loading, and U is the vector of independent control variables can be expressed. These are the real power of generators except for slack bus power. Slack bus power is state variables, and the voltage of the generating bus. The cost function is this equation. This is the normal cost function, and we use the active power which the generating units produce the active power, and A, B, C are the coefficients of the generator. This is the valve point effect formulation which I mentioned before, and also we use the penalty function for the violation of the active power in the generating. If generator produce much power than the Pmax, we use this penalty function, or it's produced less than the minimum power, also we use the penalty function. These are the power flow equations. This is the equality power flow equations, and these are the inequality constraints. We have the produce between the active power between maximum and minimum, reactive power between maximum and minimum, voltage must be between maximum and minimum, and transmission lines MVA must be less than the maximum, and transformer top settings between maximum and minimum. These figures show us the OPF with heuristic methods. First, our algorithm initialize, and then we use Newton-Raphson methods for the power flow. Then our algorithm checks if there is any constraint violation. If yes, we ask is it generation violation. If it is yes, we apply penalty function I expressed before. If it is not a generation violations, we stop the algorithm and we restart, because it must be between the limits. Then if we continue the algorithm, we calculate the fuel cost, then decide fitness value, select best solution. If we satisfy the iteration limit, if we reach the maximum limit, we stop the iteration. Then, if not, we going another step for iteration. I will mention about the algorithms which I used in my study. Genetic algorithm is a new population using gen of individuals belong to previous population. The algorithm is initialized with random solutions. Then GA chromosome string is selected from previous generation for reproduction. And reproduction works with crossover operators. Main purpose of the crossover is getting best feature of parents and obtaining more quality offspring. Mutation is the arbitrary change independently in gens of a chromosome. After we use selection process to get the new solution, better solution. Differential evaluation also has the similar process. They has a random initialization and mutation process, then crossover and selection process. PCO, particle swarm optimization. Each individual in PSO solution is called a particle in searching space. It corresponds a bird in the swarm. When a particle moves, it sends its coordinates to function of defined fitness value. X is the position of the particle, V is the velocity of the particle, and again it has a random initialization. Position and the velocity of the particles are updated by best solution P best and G best. Then we find the global solution with this formulation. Then we update the results, and we find the new better results. If we have better result, we use new solution or we use X solution. Article B colony. This is corresponds to bees. Bees moves in the hive. We have three types of the bees in the hive: employed bees, onlooker bees, and scout bees. Employed bees share the quality of the information of the food source. Onlooker bees in the hive, they get the information and decide which food source they will go. Scout bees are randomly scattered to find the new food sources, and the process of the algorithm is random initialization again, producing new food sources which employed bees determine. Defining the quality of the source, we define the quality of the source, and we determine the new source which bees have to go. And the case study, we use IEEE third bus system. Common parameters, population size and iteration number are the same for each iteration. It is 20 for population size and 100 for iteration number. The specific parameters are each algorithm are here. G parameters, selection function, crossover function, mutation function, and crossover fraction are selected like that. DE parameters are scaling factor and crossover rates. PSO parameters, inertia weight factor and acceleration constant. We use that numbers for the simulation. And ABC parameters is limit is 100. And these are our results. As we see, PSO is the best has the best results. It's the minimum fuel cost results. Differential evaluation. And GA, genetic algorithm, is the second one. And ABC and PSO they are the proportionally worse algorithms. As we see, while GA, DE, and ABC continue to converge, PCO has the best value, and then it did not converge again. PCO continue to converge, and these are the similar also. If we stop the iteration at before the 10th iteration, as we see, the PSO is the best algorithm, but we used 100 iteration number, so after the 100 iteration, the DA differential evaluation is the best algorithm for the solution of the OPF. These are the bus voltages. These are the bus number and voltages. As we see, the bus voltages are not so different from each other. They are very similar, but they are not lower than the 1.95 per unit value. These are also results. The fuel cost is 9.18 is DA is the best, is the minimum result, and then GA, and then PSO and ABC. These are the iteration times. As we see, GA is the best one, and second one is the DE solution of the OPF. As conclusion, simulation results demonstrate that differential evaluation and genetic algorithm are the cost-effective algorithms for solving OPF with valve point effect problem. Whereas GA has the fastest iteration time, DE has the minimum fuel cost results. Although these algorithms have the best simulation result from objective function, which is fuel cost point of view, they have high line losses rate. Although PSO has the high initialization value, it reached the optimum solution at early number of iteration. Finally, DE is the most effective algorithm with good iteration times. That is to say DE and the GE are the most cost effective than the swarm-based algorithm PSO and the ABC solution of OPF with valve point effect. Thank you for listening.
Thank you very much. Thank you. Question? No question? Okay, thank you very much. This time is going to be fast, and we will have to look at one paper sets again. And the last paper will be from the session 6B1, and that's Mehmet Honor. Will be performance comparison of particle swarm optimization, differential evaluation, artificial bee colony algorithms for fuzzy modeling and nonlinear systems. Please go ahead.
My name is Mehmet Konar. I graduated with Erciyes University in Turkey. Title is Performance Comparison of Particle Swarm Optimization, Differential Evaluation, Article Beacon Algorithm for Fuzzy Modeling of Nonlinear Systems. This study presents the result of the nonlinear system modeling approach based on the use of the fuzzy rules optimization, different population based optimization algorithm. Fuzzy rule based models with different number of the rules are used to describe some nonlinear systems in literature. Firstly, parameters of fuzzy models are determined by article beacon algorithm. To demonstrate the efficiency on the of the ABC algorithm, its modeling able to is compared with the other two powerful population-based algorithm, particle swarm optimization (PSO) and differential evaluation algorithm. Simulation results show that successful model performance with good discrete able to in modeling of nonlinear system or complex system can be obtained by using one of the population-based algorithm in design the fuzzy rule-based models. Fuzzy rule-based structure used in the studies. First rule, second rule, a sample fuzzy rule base with two rules, and parameter matrix of define the membership function and rules, input membership function, and input to output adjustment parameters. In study simulation results, in studies two numeric model problems given in the literature are used to investigate performance of the algorithm for identification of the fuzzy models. One problems, antenna model problems, two problems, Bach-Jenkins gas Franz problems. For study, this studies three algorithms are testing by using different number of the rules, such as 2, 3, 4, 5, and 10, and different maximum cycles or iteration cycles, one azimuth and one azimuth 500. The paper presents the best result of the studies for colony size 13. The result obtained for ABC based fuzzy models are compared with those PSI and differential evaluation algorithms. The essential of the problems given in the literature is to estimate bandwidth and the rectangular microsite antennas by using the measuring dataset. It is in here antenna problems, input or output show. Therefore, antenna problems, 3 input and 1 output used to studies. Such as case number of the optimization is 13 of rows in the optimization fuzzy models based on the used algorithms. That in here used to train data number is 27 and test number is 6 as used in the literature. Table 1 present minimum MSI variable for different fuzzy rules based model obtained using the algorithm. In here, rule number 2, 3, 4, 5, 10, and dataset train dataset and testing dataset. Algorithm ABC and DIE and PSO. Maximum cycles, iteration cycles in 100 and 105, 1000 and 1500. We select all models on 10 rows. For fuzzy models, MSI is 0.0201 and DEI and PSOI in shown. Figure 2 shows figure 2 show the output of the fuzzy models and measuring bandwidth and PSI and ABC and DIE showing. Figure 3 show in here iteration to MSI variation, MSI and iteration. In here ABC algorithms iteration, MSI to iteration, DIE MSI to iteration, and PSO MSI to iteration. Table 2 shown comprise of your study and other methods in the literature for untamed problems. Our study ABC, DIE, PCI, and Mamdani models reference 24, Sugeno models reference 24, ABC result. Second problem is Bak-Janssen gas furnace problems. Consist of dataset include input-output measuring 296 per used to optimize a fuzzy rules maze model. In here, Bak-Janssen problems in detail, and Bak-Janssen problem is result rules 2, 3, 4, 5, and 10, and algorithm ABC, DIE, and PSO. Iteration. We select the minimum iteration ABC 0.1365, DI 0.2078, and PSO 0.1542. And figure 4 show output of the originals and fuzzy models with 10 rules for Bak-Janssen problems. PSO, ABC ve DIA models results. Figure 5 show iteration the MSI variation of the algorithm-based fuzzy model for Bak-Janssen problems. ABC, DIE ve PSO fuzzy models. Table 4 showing compressed of the our study on the other methods in the literature for Bak-Janssen problems. Other methods here, and our studies ABC, DIE, PSO 10 rules. Conclusion: the paper presents a useful investigation about the effect of the population based on the 3 population algorithm ABC, the PSO algorithm in the fuzzy modeling on the nonlinear system. We used two problems, Bach-Jenkins and antenna problems. Fuzzy rule-based models in different rule number optimizing the algorithm is applied to popular nonlinear system given in literature. Simulation results show that they are able to define the nonlinear system complex system. On the fuzzy rule-based models can be simulation improved by using the differential evaluation and article B algorithm, essential and competitive solution for difficult engineering problems can be produced. Thank you.
Okay, thank you very much. Any questions? As a mathematical approach to different methods, therefore hard to understand. Okay, thank you very much. Thank you again. Okay, once again, thank you, presenter. The other presenter disappeared probably. And then now I will invite you for the welcome party at 6 o'clock. Professor Valinevicius, do we have to use a formal suit or just we can change clothes? What do you think? So it's up to us, but probably the formal suit. Okay, we will meet here in front of the hotel and then we walk. Okay, thank you very much and see you.